So we have a straightforward experiment today involving chromatography. The idea is if you're doing synthesis, especially if you're doing organic synthesis, one of the problems you run into is often in an organic synthesis you don't get one product, you get a bunch of products. And this is routine. And so the result you get, the product you end up with, is actually usually a mixture of things, including the stuff you actually want. So one of the things you have to do is separate all the stuff you don't want from the stuff that you do want. And chromatography is one of the ways that you can do this. Chromatography basically involves two components. A solvent that you are dissolving the material you're trying to unmix together in, and some kind of substrate, some material that the solvent is moving past that interacts with the mixture of materials in the solvent. In this case, the solvent is referred to as the moving phase because the solvent is in fact in motion. The substrate is usually referred to as the stationary phase because the substrate is not moving. It is the solvent that is moving by the substrate that produces the separation technique. Suppose we have a mixture that includes three compounds, A, B, and C, and they're different materials, although they're all soluble in the solvent and they're perfectly happy to be in solution with the solvent. But they have an interaction with the substrate. It reaches out and grabs onto them temporarily as they go by, and this is where we get the separation from. If, for example, compound A has a very strong interaction with the substrate, then as it moves past in the solvent, it will from time to time attach itself to the substrate, and it will stay there for a short period before moving back into solution and moving on down. But every time it interacts with the surface, that slows it down and delays how far it moves, while the solvent continues to go past. If the compound B has less of a tendency to interact with the substrate, then it won't get stopped and held on to as often or for as long as A will. And so it'll make more progress as the solvent carries it along. And finally, if C only weakly interacts with the substrate, it is only going to get caught for short periods of time and only occasionally. And so it'll spend most of its time, in fact, going along with the solvent. And the effect we're going to see when we run the mixture is these interactions with the surface will slow each of the components down and will cause them to spread out. The C, the one that is weakly interacting with the substrate, will carry almost all the distance that the solvent covers. Meanwhile, B, which moderately interacts with the surface, will cover about half the distance that is covered by the solvent. And meanwhile, A, which strongly interacts with the surface, will only manage to travel the short distance as the solvent moves along. The result is that our three components are going to end up at three different places on our substrate when we are done. The first one, the A material, is going to be only about a third of the way. The B is going to be about halfway, and the C is going to be 90% of the distance covered by the solvent. So we end up talking about an RF. And that's simply the distance that is covered by the compound compared to the distance that's covered by the solvent. And like we said, we can see approximately that the RF for the red compound, that is A, is going to be about 0.3. The RF for B is going to be about 0.5, and the RF for C is going to be about 0.9. And so we'll have separated our components. And this is how you characterize the compounds in chromatography. The ones which have small RF distances are strongly interacting with the surface, whereas the ones that have larger values are the ones that are moving the most with the solvent. One of the challenges in chromatography is, in fact, to pick the right solvent. You want something that, in fact, does dissolve all the components of the mixture, but you want them to be sort of borderline. That is, you want them to have some reason to interact with the surface. If they are all extremely soluble in the solvent, they will not interact with the surface and you won't get much of a separation. On the other hand, if they all interact really strongly with the surface, then they won't move at all, and again, you won't get any kind of separation. So one of the challenges in chromatography is to pick the right moving phase and the right stationary phase in order to get a good separation of your mixtures. In today's experiment, you're going to be looking at water-soluble dyes, that is, not permanent markers. And what you'll be using as a solvent to begin with is water. Since they're soluble in water, that should be a good solvent for dissolving them. And you'll be working with a piece of paper as your substrate and see if you get a good separation. If you do, then you'll have to calculate the RF values for the different dye colors you see as a result of the experiment. On the other hand, if they do not separate well, we'll have to try some other solvent.
So the first thing we're going to have to do is we're going to have to prepare our samples. We've already prepared our strips and marked 1/4 of an inch up where we want our dot, as well as identifying the strips with the letters O, P, V, and VL for orange, purple, brown, and black, respectively. We're now going to put a dot on our starting line for each of our materials. And after that, we can put them into the solvents and see what happens. So we have our test tubes, each with the water at the bottom, and we're now going to put each of our strips into the test tubes and let the water begin to move up. After we drop the strips in, we'll seal the top so we don't have all the water evaporate, and then we simply have to wait and see what happens. Experiment running for several minutes, and you can see that the water is moving up the column and that the dots of ink have begun to spread out as they go up the line. They're not nearly to the top yet, so we're going to have to keep going from here, but things are going along. As you can see, the solvent has made it almost to the top of the filter paper, so the time has come to take the strips out and measure how far the different parts have moved. As we take each of the strips out of the test tubes, we have to lay them down and mark with our pencil how far the solvent actually got. That's because that's the total distance we are comparing how far the dots moved when we're trying to get our RF values. Unfortunately, as you can see, we're running into a problem with our experiment. The dyes did all move, but unfortunately they all moved almost the whole distance that the solvent moved. Apparently they were not they were so soluble in the water that they were not interacting well with the filter paper, and so we weren't getting a good separation. That means we're going to have to try again and use some other solvent to run the experiment. Well, we tried using just water, but we did not get a good separation by our chromatography technique. So we're going to try a different solvent. This time we're going to try a mixture that is 60% propanol and 40% water. This should be less polar and the water-soluble dye should be less soluble in it. So we again have to produce our strips and add our dot to each of our piece of filter paper, just as we did in the first try. So now we're going to put our stripes into our propanol and water mixture, drop them in, and again seal them up, and let them start spreading up the sides of the filter paper. Again, it's been several minutes, and as you can see, the solvent is moving up and the dots are moving up as well. So things are going along. Finally, the solvent has gotten up near the top of the filter paper, and so now it is time to again take the strips out, mark where the solvent got to, and figure out how far each of our dots moved on the filter paper. It looks like the solvent for the black strip moved about 5.8 centimeters, and we seem to have 3 dots. We have one red that seems to be centered about 3.1 centimeters. We have a green dot in the middle at about 4.2 and a black dot at 5.1 in our sample. So those are the colors that make black. Again, the solvent seemed to move about 5.7 centimeters. We got a dot that seems to be yellow in color at about 2.5 centered. We got again a red dot at about 3.5, and finally a light blue that's centered apparently about 4.8 on our scale. For our purple dot, we again seem to be getting 3 colors. Again, a light red that's down around 3, and a blue at about 4.5, and sort of a light colored purplish at 5 for the sample. And those are the ones that are making our purple color. And finally we move to our orange dye, and our orange dye seems to consist of only 2 colors. We have a yellow dot that seems to be centered about 2.5 and a red area that seems to be centered about 3.5. And so now we have measured all the values and motions of our different colored dots. We can now go on and calculate our RFs for the different colored dots.
So that brings us to the end of today's experiment. You're going to have to figure out the RFE values for each of the different dots of color for the different inks. And after that, you can go and have a nice day.